Hello, my name is Dr. Maria Weber, and today I'm going to work through an electrostatics problem. So suppose we had three charges in line on the x-axis at positions of the first charge at a position of 0 on the x-axis, so it's sitting at the origin. Our second charge is at a position of 1.5 meters from the origin, and our third charge is at a position of 2.6 meters from the origin. And each of our charges has a different amount of charge. The first one has 36 microcoulombs of charge. The second one has negative 30 microcoulombs of charge. And the third one has 36 microcoulombs of charge. And so the question that we're going to answer is, what is the net force in newtons on this third sphere right here? So we are looking for F3. What does that equal to? So remember that forces are vectors. And in order to get the force on charge 3 here, we have to sum up the forces acting on charge 3 from charge 1 way down here at the end. So we call that force sub 1, 3, the force of charge 1 on charge 3. And we have to add that up with the force of F2, 3, the force of charge 2 acting on 3. Now, forces are vectors, so they have a particular magnitude and a direction. Here, all of our forces are acting along the positive x-axis, so our answer, we're only going to have to deal with the x component of these forces in order to get our answer. Now, remember that these forces between charges are attractive if the if the charges are of opposite sign, and these forces are repulsive if the charges are of the same sign. So if I go ahead and draw the direction of the vector for force 1, 3, the force that charge 1 exerts on charge 3, since charge 1 is a positive force and charge 3 is a positive force, those forces are going to be repulsive. So force F sub 1, 3 is going to be pointing off here along the positive x direction. Okay? And then if I think about F2, 3, the force that charge 2 exerts on charge 3, well, charge 2 is a negative charge 3 is a positive charge. So those are attractive forces. So the force that charge 2 exerts on charge 3 is going to be pointing toward our negative charge 2. So it's going to be pointing in the negative x direction, negative F2, 3. Okay? So that's what these forces look like when we draw them in their vector form. And now we need to get the magnitude of these forces. So the magnitude of the force that one charge exerts on another, the magnitude of that force is equal to the constant K, the Coulomb constant, sometimes this is called, times the absolute value of one of the charges, times the absolute value of the second charge, all divided by the distance between them squared. So in order to find the magnitude of the force that charge 1 exerts on charge 3, okay, that's going to be equal to our Coulomb constant times the absolute value of charge 1 times charge 3 all over the distance between them squared. Okay? So if I go ahead and plug in those values, our constant K is 8.99 times 10 to the 9 Newton meters squared over coulombs squared. And we're going to multiply that by the charges on both of these particles. So we're going to multiply that by 36 times 10 to the minus 6 C, because a microcoulomb is 10 to the minus 6 coulombs. And then we have to multiply that, so that's the charge for Q1, absolute value of it. And then we're going to multiply that by the charge on Q3, which is also 36 times 10 to the minus 6 coulombs. 10 to the minus 6 is a microcoulomb. And then we're going to divide that all by the distance between charge 1 and charge 3. And so that distance is going to be 2.6 meters. So do we divide that by 2.6 meters squared? Okay. So if we plug those values into our calculator, we'll get that the magnitude of the force that charge 1 exerts on charge 3 is going to be equal to positive 1.72 newtons. Positive because we know that that force here is pointing in the positive x direction. Okay, so F13x is this quantity right here. Okay, now we're going to do the same thing except for F23, the force that charge 2 exerts on charge 3. Now I'm going to leave F13x boxed down here. I'm going to repurpose what I just wrote up here and erase the 1 here because now we're looking at force 2, 3, and that's going to equal to our charge Q2 times Q3 all over the distance between them squared. That's going to be equal to 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. That's our Coulomb constant. And we're going to multiply that by the charge of Q2, which in this case, absolute value, again, is 30 times 10 to the minus 6 coulombs. We'll multiply that by Q3, 36 times 10 to the minus 6 coulombs, and we divide it by the distance between them squared. So the distance between Q2 and Q3 is going to be 2.6 meters here minus 1.5 meters. And then we square that. We plug those values into our calculator. We get that the magnitude of F23 is equal to 8.02 newtons. But if we look at the direction in which our vector is pointing, F23 is pointing towards Q2 along the negative x-axis. So the component of the vector F23 in the x direction is negative 8.02 newtons. Okay? So now we can use these two components of our forces, sum them up in order to get the magnitude of the force acting on charge 3. So if I go back up here, F3x is going to equal to F13x. So 1.72 newtons plus, well actually we have negative 8.02 nutons here, negative 8.02 newtons. And if I take 1.72 newtons minus 8.02 newtons, then I get that my resultant answer is minus 6.3 newtons. So the net force in newtons on my third sphere is going to be negative 6.3 newtons, negative because the sum of all the forces acting on Q3 is actually going to be pointing along the negative, towards the origin along the negative x-axis. So this vector that I just drew here is going to be F3. All right, so that's how we solve these types of problems when we've got our charges lined up in one dimension along the x-axis.